see other questions in Slack. I don't know if Yuri, Matteo, Nicola, you spot other questions that you want to discuss live.
There are some coming up now. So, for example, it's been if you have systems where the band gap is not known, how do you know when to use DFT plus U, DFT plus U plus V, since you have nothing to compare the calculations with? Let me spend some words and then maybe pass it on to Yuri if he wants to comment as well. Well, basically, we have HP as a nice instrument to try, and we try to compute them, maybe do some step of self-consistency, at least if it's not too expensive, and we get an idea. Then, of course, there is this problem of multiple local minimum that your system can get with when using finite Hubbard U and V's, and there's always a chance that the global ground state is something else than what you're looking at, but at least you have somewhere where to start your investigation. I don't know, Yuri, if you want to add something.
Oh, no,
anyone
totally,
else?
I totally agree with you. Just maybe a little addition that DFT plus U plus V is more accurate. So I would rather trust to DFT plus U plus V rather than DFT plus U. Maybe it's not always better, but I would rely more on DFT plus U plus V. And then just a reminder that neither DFT plus U nor DFT plus U plus V are the methods for band gaps. Tomorrow you will learn about Koopman's functionals. So those are the methods, those are the functionals for accurate band gaps, while Hubbard functionals only improve band gaps. Yes, so that's the message.
Thanks, Yuri and Matteo. Then I don't know if you want to spend a couple of words on what is the difference between the Lichtenstein formulation and Dudarev's formulation.
So I mentioned very quickly in my presentation that the Lichtenstein formulation came out in '95 and is based on a sort of Hartree-Fock-like expression of the Hubbard correction that has effective Hubbard parameters linked to the atomic average and with some atomic parameter. The Dudarev calculation, the Dudarev expression of the plus U function came out a little later, still rotational invariant for rotations of the atomic orbitals on the same atom. It's simpler, of course, and can be obtained from the first by neglecting the anisotropies of these effective interactions. So, in principle, the first one is more accurate, and there are systems, I guess, but I don't remember which one. That for which using one or the other makes a little bit of a difference. But yeah. In most codes, I think there is the Dudarev nowadays implemented.
Okay,
Quantum Espresso has both. But I think the Lichtenstein doesn't have all the features implemented. Like, for example, probably you don't have forces implemented or stresses, not to speak of phonons.
Yeah, thanks for clarifying. So, I don't know. I don't see. Well, there's another question. Wait a second. Yeah, this I would pick. How orthoatomic Hubbard projectors used in QE and PAW formalism used in VASP are different. They optimize U using HP in QE. Can be used as the same in VASP, right? As mentioned in the talk. Perhaps, yeah, we can further stress this point.
Yeah, I can take this question. So in QE, you have orthoatomic orbitals. In VASP, you have PAW projectors. So it's two different type of projectors. So in Hubbard U is different for two codes. So the optimized U using HP in QE can be used in VASP correctly. It can be used because in QE you use orthoatomic orbitals or atomic if you want, while in VASP you use completely different orbitals. So it's not compatible. You can't do that.
So here, there's a belief that I have since quite some time that may be unfounded. That is, perhaps if we take different set of orbitals and then we compute the linear response consistently on these two different sets, I would expect eventually that the final properties we are evaluating, also the bands, or may not be that different. The U values are going to be different, but the final properties may not be that different. I don't know if is this also your feeling? This comes a bit with the experience on Koopmans, where one also has the screen parameter with orbitals of different size, but it's just a good feeling.
Yes, that should be the case, I think, provided that the two representations of the two sets of orbitals that you use span an equivalent space, so they carry equivalent informations, basically. Then whether that is true in practice also depends on these details. So, and regarding the fact that, what Yuri was discussing earlier, PAW versus atomic wave function, another difference is that PAW projector only live within the core radii, right? So
sorry, could you repeat the last part?
The PAW projectors aren't those living only inside the core radii of each atom, so they don't extend beyond that. So that makes quite a difference with using atomic wave functions instead.
Yeah, but actually it's very good comments, but in practice we tested this idea and actually we found that orthoatomic gives more accurate results than atomic. It has a physical meaning also because when you use atomic orbitals in the overlap regions, you apply the Hubbard U correction twice. And actually in practice, we do find orthoatomic to be more accurate. So this hypothesis actually in practice not really working from what we learn from our testing.
But that I see as a different issue though, because, the atomic basis set basically carries a mistake with it in the sense that forces you to count some electron twice, which is not right. It's not the results of a rotation, basically, or a unitary transformation within the same manifold.
Yeah.
So.
Yeah. But if we just come back to my lecture of this morning, I just gave a few examples. Like this is actually again the band gaps for different materials, and which shown that when we compute Hubbard U with HP code and orthoatomic orbitals, we get band gaps much closer to experiments rather than if we use atomic orbitals and U computed with HP, it gives way off the band gaps. So this is one example showing that orthoatomic is better than atomic. Another example was actually sorry, let me go next slide. Yeah, this manganese dioxide polymorphs. Again, if you remember my lecture, I showed that orthogonalized atomic orbitals are more accurate for the relative total energies or for band gaps. but also coming to, okay, for voltages, we didn't test with atomic. We always use orthoatomic and it's very good. Yeah, for at least for these two cases like band gaps and relative energetics, for a couple of cases we found orthoatomic to be more accurate. That's why we recommend to use orthoatomic. Yeah, sorry, that was just my opinion, but
no, thanks for pointing it out.
Yeah. There is also another very nice paper where not from our group but from other group, showing that they took quantum espresso, VN2K, and VASP, which all have different projectors, and they used empirical U, 1 EV, 2 EV, 3, 4, 5, up to 10, and they saw that exactly the same value of U with different Hubble projectors gives different band gaps, different magnetic moments. It's also showing the importance of type of Hubble projectors. No, it's a very interesting question. And often people overlook it, actually.
So there are two more questions that may be worth going through. That is, non-collinear calculation is implemented only with the T plus U, with LDA plus U kind equal 1, right? Is this true?
Yes, that's correct.
Yeah,
but in our group, we have one PhD student, Luca Binci, and he's implemented the non-collinear implementation for DFT plus U, LDA plus U kind 0. Yeah, which is no longer existing as input keywords, LDA plus U kind. This disappeared in the latest versions. But LDA plus U kind equals to 1 corresponds to Lichtenstein formulation. It was non-collinear for a long time. But now we have also Dudarev DFT plus U formalism in non-collinear, but not yet public. It will be public.
This is, I mean, following what Cesare Franchini did.
Yeah, I think it's very, yes. I think it's very similar and probably exactly the same. I'm not sure. I need to ask Luca. Okay. But this should become public in the future releases of Quantum Espresso.
Okay, great.
There's another question that is, suppose there is one well-known system, Europium TiO3, for which U is known for Europium and is 7 eV. And there is one system that has basically substitute titanium with hafnium, but the oxidation state of Europium is the same in the two cases. What is your guess about the value of U? So can one think of transfer the value of U from one case to another? So we are just changing another transition metal without changing the oxidation state, or is it unpredictable and it's best always to recompute? Or better, it's best always to recompute, but just for our own physical understanding, what would you expect?
I would say, I mean, hard to say, hard to guess, in the sense that in principle, yes, the U could be similar to the other material, but in general doesn't only depends on the oxidation state. It might depend also, there is some structural distortion or electronic distortion. I mean, electronic state might not be the same, and I guess we've seen also from my presentation that also the oxidation state concept is a nominal one, is an empirical one. What do we have in crystals? I mean, we have a continuous change of occupation state, and even those are not univocally defined. So there's many methods to project states on many manifold, and they all give different numbers in terms of oxidation state, and they would, I would guess, they would change slightly. So how close, and the U is also consistent with the definition of the occupation state, occupation matrices that you use. So given all these forwards, I mean, the U will depend on the electronic structure of the material. So hopefully it doesn't change too much, but some slight changes are possible, I would say.
If you find 7 EV in one case and 1 EV in the other, perhaps.
Yeah, that's a bit too much for something that keeps the oxidation state at least nominally, but some smaller change could happen actually.
So yeah. I think that the issue of frozen phonon versus linear response, we have already discussed also a second time with Andrea, so I wouldn't go through that question again, though it mentions Raman, but okay. So I think we had half an hour of Q&A. Perhaps that could be okay for the day. It was a long day today as well. I think very, very interesting, both theory-wise and hands-on-wise. So perhaps if there are no other urgent and impelling questions, I would close the session here. Not before actually having thanked again all the lecturers and all the hands-on tutors and tutors behind the scenes. Any other comment from the organizers? I think that besides this reschedule of Renata's talk tomorrow, all the program of the day stays the same. So we'll reconvene at 9 a.m. Well, let me thank again Andrea also for giving this very nice lecture.
Thank you very much.
Thanks, Andrea.
Thank you.